We're on the last day of our new material for the logarithmics unit, and the good news is we're going to be solving equations, and we're going to be using a lot of our old techniques to solve equations. Everything we learned in algebra. More good news is that it doesn't involve any trig, but it does involve a lot of algebra. So, brief review of the kinds of things you can encounter. There's no magic to solving these equations. You kind of have to analyze based on the equation that you're given what, if any, of the tools you can use. And you wouldn't necessarily solve these in the exact same way I would, but you could still come to a correct solution. So let's begin with fractions. Yes, you can have fractions pop up in these equations, and you have to know how to work with your fractions, and that's from basic algebra or working with our rational expressions back in Unit 2. Everything you remember about solving, in other words, getting the variable term isolated, and once you have the variable term isolated, then getting that variable by itself. Everything you remember about PEMDAS, you have to do things in the proper order. Looking inside of parentheses first, taking care of anything that's happening inside of parentheses. Then looking to exponents, taking care of exponents. Cleaning up both sides of an equation. Moving on down, everything you remember about logs and exponentials, and this is fairly recent information. We know we can go back and forth between logs and exponentials. We learned a lot about properties of logs and properties of exponentials. We learned how to change form. We learned how to expand and contract the laws. When you have multiplication or division or exponents inside your argument, how you can deal with each of those. Or if you have a long expression with logs in it, how you can contract it to a single expression. And we learned how to change base, so that when you come to the point where you need to get a number out of your calculator, you've got a number base, you've got a number argument, and you need something out of the calculator, you can use a change of base to get there. A couple of other things, not more out of the category of basic things that we've learned in algebra already, but take a look at this statement here. If you have a log base 3 of some argument on the left and you have a log base 3 of some argument on the right, then I hope you would tell me that the only way this can be true is if x is equal to y. You kind of saw that an equivalent for that back in our exponentials unit. If you saw 3 to the x equals 3 to the 5th, you knew that the only way for that statement to be true was if x was equal to 5. So it's really the same idea going on here. Moving on down our page. How would you know that the argument of a log function can never be 0? And a question that goes right along with that, how would you know that the argument of a log function can never be negative? Well, one of the first ways that you can know that is by taking a look at your basic log function. I've graphed for you a log base 10 of x, and if you look at this function, you know that it does not exist in quadrant 3, it doesn't exist in quadrant 4. For that reason, we know that we won't ever be putting in any negative x values into that argument. Its function doesn't exist there. And also, we've talked about the asymptotic behavior. There is an asymptote at the y-axis for this function. It's a vertical asymptote, and when you have an asymptote, it means your function gets infinitely close to it, and then it moves a little bit closer, and then a little bit closer, and it just does that forever. So it never actually touches 0. That means not only can I never have a negative number here, but I can also never have a 0 there. Okay, let's take a look at this screen here, why we have to check our answers. Well, sometimes we're solving for bases and we might come up with a 0. And if we're solving for bases and we come up with a 0, we got a little bit of a problem, because you cannot take a log base 0 of 5. You'll get an undefined result. And as we talked about already, if you try to calculate an argument of 0, you know you're not allowed to put in 0 for an x value. That's an asymptote there, so you'd also get an undefined value. A second algebraic way of looking at either of these options, or all three of the options, is to try to turn it into an exponential form. This would say 10 to the x equals 0, and I would challenge you to come up with any value for x that's going to make this true. Likewise here, 0 to the x power is equal to 5. That would be interesting for you to try to turn that into some value, some legitimate value for x. And this last one here, we'd be looking at 0 to the x equals 0. You might think, well, x can be 0 in that case, but if you ask your calculator what 0 to the 0 power is, it's also going to tell you that's undefined. That's an indeterminate form. There is no such thing as 0 to the 0 power. With that, we'll get busy looking at some examples of solving log equations. And again, before I start, I want to just emphasize that the way you approach these problems might not be exactly the same way as I approach them. There's often several ways to do things when we're talking about algebra. I'm looking at 2 log base 5 to the x equals log base 5 to the 16. Well, I'm going to take that 2 and I'm going to swoosh it back up as an exponent. I'm going to turn the left-hand side into log base 5 of x squared. Equals, on the right hand side, we're still looking at log base 5 of 16. And now I can use that, what we talked about on the first slide there, is the only way for this statement to be a true statement is if these two arguments are equal. So let me set x squared equal to 16. And it's a quadratic equation, so I'm going to bring it all to the left hand side, and then I'll factor it. X plus 4, x minus 4 is equal to 0. That will give me an x equals negative 4, and it'll give me x equals 4. But whenever we're solving log equations, we want to check because we know that we can have illegitimate solutions here. We should know, if you look right here, that the argument of a log function cannot be a negative number. So we're going to have to reject that answer, and our only answer here is x is equal to 4. So yes, you will need to check your work so that you're not missing any of those functions. Remember, the domain of your log function starts at 0 and goes out to positive infinity. It doesn't touch a 0, and it doesn't touch infinity. So this is the domain of that log of x, and you want to keep that in mind every time you solve. If your solution is not contained in this domain, then you have to reject it. Second example, and now we've got 2 logs on the left. So if we have 2 logs on the left, we could combine them into one single log or contract them into one single log. Be careful when you do this. Make sure that your bases are the same. Remember, those laws of expansion and contraction are all about keeping the same base on both sides. So let's begin by combining this into log base 3 of, well, we were adding the 2 logs, so that gives us multiplication inside the argument. Now that's a 5x is equal to log base 3 of 7 plus x. And again, if we take a look at this statement here, if you look at the log base 3 and the log base 3 and they're both equal, that must mean that those 2 yellow arguments have to be equal. So we'll just set them equal to each other. 5x is equal to 7 plus x, and now you got one of those second grade algebra problems to solve. We'll just subtract x from both sides. Gives me 4x is equal to 7, divide both sides by 4, x is equal to 7/4. And we have a couple of different ways of checking this. The fastest way I'm going to think of is by using the Inspire. If you are required to show checks on your paper, then you'll have to show the algebraic check. If you're not required to show an algebraic check, then you don't have to. I'm going to bring up my handheld here onto the screen, and so we're checking our original equation. Now we do have irrational numbers here. We've seen logs involve irrational numbers a lot of times. So what I want to do is I want to store my answer, and then I'll type in both sides of the equation separately and see if I get the same result. So I'm going to put 7/4 into x, 7 over 4. We're going to be storing that into x. And once it's there, then we'll type the left-hand side. Now when you type in log base 3 of 5, remember that you have to type that in as you have to use your change of base formula. So we'll bring up a fraction. We'll type in a log, and we'll put the 5 on top. Remember, the base goes on the bottom. On the bottom, we're going to put in the log and the 3 down the bottom. And that's one part of the left-hand side. I'm going to move out of that fraction, type a plus sign, bring up another fraction, and now we're going to type in, now we already have the number stored for x, so you're okay typing in an x here. On top we'll put in log, and we'll move into the argument, put an x, go to the bottom, a log, move into the argument, put a 3 in there. Well, with my solution, the left-hand side gives me 1.97436. If I had any issues with negative numbers here, if I had any answers that I was supposed to reject, it would pop up right here. I would get an error or an undefined coming out of the calculator when I checked it. So it's a great way to pick up those roots that you're supposed to reject. On the right-hand side, let's see if this one works out. We're going to do a change of base in here. So on top of the fraction, I'm going to have a log, and in the argument a 7 plus x, and on the bottom again the log. And remember, when you're doing change of base, the base goes on the bottom, so I'm putting the 3 in the argument on the bottom, and you're going to see the exact same number pop up, which tells you that the left hand side and the right hand side are equal, and so that number 7/4 is good. We didn't have any problems with rejected roots. Didn't expect any problems with rejected roots because we didn't have any negative or zero answers there. Moving on down to our last example. Oops, get it back. Last example on this page. And I'll start by noticing, well, good, I've got base A's all the way across. So let's think about our rules of contracting here. If I have two log base A's, then I can rewrite this to start off with as log base A, one word log. And if I was adding those two, then that means I'm multiplying the two arguments. Now be careful here. This is an x, and this is binomial x minus 2. When you multiply those two things, you have to distribute. So inside my argument, it's going to become x squared minus 2x. And on the other side, I've still got that log base A of x plus 4. Okay, we've got a true equals in between these two, so the only way to force these to be true is if I force the two arguments to be equal to each other. X squared minus 2x equals x plus 4, and now you see a quadratic equation developing out of this. I'll subtract x and subtract 4 from both sides, which will leave me with equals sign there, x squared minus 3x minus 4 is equal to 0. And remember, when you develop a quadratic equation in the middle of a problem, oftentimes it's going to be factorable. So check that first before you get busy completing the square or quadratic. You know that time is an issue on your unit tests. We're going to, oops, white doesn't show up. We'll fact an x here and an x here, and I'm going to put a 4 there, make that one negative, put a 1 here, make that one positive. This is going to give me two answers. It gives me x equals 4, gives me x equals negative 1, and you're probably guessing right now that we're going to end up rejecting that x equals negative 1, but let's ask the calculator to check it for us. And so I stored the 4, and I typed the left hand side, got 0.90309, typed the right hand side, got 0.90309. Let's next store the 1 and see what happens. I'll just do copy paste. And I can see when I store that negative 1 that I got and I type that left hand side, I've got a little problem. It tells me right there that that negative 1 is outside the domain of my function. So I'm catching the fact that I can't use it. You might have asked the question, I'm just going to dismiss this, you might have asked the question, why did I just use log base 10s? Well, as long as I have the same base across the equation, this should work for absolutely any value, any base, but you do have some exceptions there. You could choose any positive value for that base of A, so I'll just use 10 because it's easy to type on my calculator, just let it default to 10. But you wouldn't be able to choose negative values A or value of base of A equal to 0. And that's something you really don't have to worry about. The goal when you're doing these is for you to be able to solve and come up with that x in the argument. So we'll move on to the next problem here. Okay, continuing solving the equations. This one's a little bit different. We do have two logs on the left, but we've only got a number on the right hand side. Fortunately, those two logs on the left are two logs that we can combine. We're adding, and both bases are the same, so that means we can turn it into one word log, log base 4, and inside our argument now we're going to be multiplying, and now you should be recognizing that you're going to have to FOIL this all out. So let's see what the FOIL looks like. I'm going to end up with 2x, outer terms minus x squared, inner terms, the way this is lined up doesn't make it easy, but you can just follow it, minus 3x. So I'm going to end up with a quadratic here, and that's all equal to 1. Now you have a single log statement here. Here's your base, here's your argument, here's your exponent at the end. So let's say that for the first power is equal to, and we'll clean this up a little bit, it gives me a negative x squared plus x plus 6. And if we solve this quadratic, we're going to be subtracting 4 from both sides. And before you try to factor, make sure you're trying to factor with a positive in front of the x squared. So before I try to factor, I'll just change all my signs here. This will give me a plus x squared, a minus x, and a minus 2. And now I'll attempt the factoring. An x, and for a minus 2, I'm going to use a minus 2 and a plus 1. If that's all equal to 0, my solutions here, x equals 2 and x equals negative 1. I hope at this point you're suspicious of the x equals negative 1. And you'd run a calculator check on it, and I'll leave that to you. This one in the middle here uses natural logs. So remember, all our laws that we learn about for natural logs also apply to common logs and vice versa. So I've got two logs with the same base. They're both natural logs. I'll combine them into a single log. And then that means I'm going to be multiplying these arguments. So x times x plus 1 will give me x squared plus x. That's all equal to 1. I'll take my base of e, raise it to the first power. We're using log by here to go back and forth, and that equals x squared plus x. And that is an equation, it's a quadratic equation that you could complete from this point on, but that's not going to be turning out to be factorable. That e is an irrational number, so you'd have to get busy either completing the square or using your quadratic formula in order to come up with roots for this thing. And once you did that, you'd be checking both roots to make sure that they would not give you undefined results. So you could just put everything in your calculator and check that, being quick and easy. Well, maybe quick. I don't know how easy, because the answers are a wee bit complicated. But you get the idea here that everything we're doing applies both to natural logs and to common logs. Last one that we'll solve in the video here. I've got 2 log base 3's on the left, just a plain old number on the right. But if I want to be able to combine those 2 logs, what I'm going to do is I'm going to have to put that exponent up to the argument before I begin. So I'll take that 2 and put it up as an x plus 4 quantity squared, and now I'm going to be dividing those 2 arguments. So one word log base 3, on top of the log I've got x plus 4 squared. That's going to end up giving me x squared plus 8x plus 16, and on the bottom I've got a 9. That all equals 2. So at this point I would be saying 3 to the second power, which turns out to be 9, is equal to that that quadratic x squared plus 8x plus 16. And that's all over 9, don't forget. So that 3 to the second power is equal to that argument. So you're seeing the argument on this side. And since I have 9 on this side, I'm going to multiply both sides by 9, because I have a 9 on the bottom here, that quadratic, and that's going to give me an 81 on the left. So I'll have 81 is equal to x squared plus 8x plus 16, and you get busy using your quadratic formula, or if it's factorable, you could factor it, and then check your answers when you're done.